And now we'll move to some of the early career scientists talk from remotely. And so the first one will be Jack. Please take it away. I think we can see your screen and should be all good.
Hi everyone, I'm Jack Patterson. I'm a PhD student at the University of Canterbury, and today I'll be talking about some initial work regarding artificial satellite streaks in images, so those that love to shoot across our pristine size images. This is going to be a brief run-through of detection and localization methods and their efficacy on data from the CLASSI survey. And given that we've already had two great talks from Wes and Sam covering the motivations and design of CLASSI, along with some initial discoveries, I'll keep things very short here. Just to remind you with one sentence, CLASSI is an outer solar system survey looking to discover distant TNOs. So, you will likely already be familiar with streaks like this, the standard line across an image, roughly uniform in thickness and brightness. This style of streak is also very commonly seen in simulated data sets. However, in real data, we are seeing far more variety. So, streaks that vary in size, brightness, morphology, and other aspects along their length. We also see glints and flares, some of which may bleed into adjacent areas on the CCD if they're bright enough. And there are some examples there on reduced images on the left, but unfortunately, we also see the same problems in difference images as well, like on the right. So to capture some of this variety for testing purposes, just over 3,000 images from CLASSI have been manually annotated with bounding polygons around the streaks to allow us to get an accurate evaluation of the performance of the following methods. And what we'd like to have is a method that can succeed both in detection and localization of any streaks, so that at the very least, those visits containing streaks can be flagged, but ideally we can use the localization to craft a mask to apply to a given image so that we can recover as much data for science as possible. So we'll just take a quick look at two families of methods that have been tested so far, just using one main metric, which is the dice coefficient. All it is a measure of overlap between the predicted mask and the ground truth. Ranges from 0 to 1, 1 being ideal. So the first group of methods we tested are classical computer vision techniques. So these include approaches like the Huff transform, line segment detector, etc., with some degree of manual tuning. Among them, the Huff transform performed the best, but even then, its detection score is only around 0.5, not very good. That's largely due to trade-offs involved in the tuning of these methods. So optimizing for one kind of streak, like bright or wider ones, often comes at the cost of missing others. Faint or narrow features won't be picked up as well. Yeah. So next, we have the set of methods that are data-driven approaches using machine learning. So here we see a similar story, though. None of these are outperforming the top approach on earlier. But while we see the dice coefficient gives an overall picture of the performance, it doesn't tell the whole story. And in fact, it turns out that all of these methods perform very well on uniform standard streaks, but break down when faced with those with time-varying morphology and flares or brightness changes. And so for these machine learning approaches in particular, the low coefficients are actually primarily due to a high false positive rate and mislocalizations due to those effects. So here are some of the failure modes I'll just demonstrate quickly on a handful of reduced images just for illustration. So here we have a variety of misclassifications, but also even those that are correctly detected might be misaligned or otherwise only partially localized. So when we think about masking, this is the largest challenge. We want to minimize the residual streak information left over post-masking, and that is significantly challenging with these methods. So far, overall, we have a set of methods that can work in the straightforward cases, but none that can truly handle the variety of streaks found in our real data. And quantifying the impact of streaks that aren't uniform is also not that straightforward. There is another family of methods, semantic segmentation-based approaches, that I plan to test next, but it may actually be that we need a portfolio of multiple methods to apply to the images that are each specialized to pull out a particular kind of streak to achieve success overall. And lastly, the science impact is only going to actually increase in both the near and long term as launches continue to accelerate, not just from Starlink, but the other satellite ISPs that are all springing up and going into action right now. And also the next generation direct-to-cell services are also beginning to be prototyped. So continuing the testing and development of these methods will become ever more important as more and more streaks find their way into future surveys. So with that, I'm happy to take any questions. Thank you.
Sorry, unfortunately, we don't have time for questions because of the time's sake. Let's move to our next speaker.